You'll want to start off by pausing and copying this board. There's also a sheet that was handed out. It's got the old electron configuration on one side, and it looks like this on the other side. What we're going to focus on is one of my big lies. I mentioned to you earlier this week that I'm just a huge liar. And one of the biggest lies I told you is that all atoms can only have 8 valence electrons, except hydrogen, who wants 2. And it's just not true, but I want you to understand why it's not true. So what I handed out to you a moment ago, if you look on the back of the sheet you got, you'll see the electron configuration cheat sheet from a bunch of units ago. Now, of course, I never let you use that on a test or anything, but we used it to learn where the different energy levels and sublevels were. Now, look at the third period on that sheet. Look at the third period. Remember, periods are rows. What energy do all of the elements in the third period have? I'm looking for a number. What energy? 3, right? There's a 3s and a 3p. Now, look here. Look here. Something cool. If I'm sulfur, all right? I'm sulfur. I don't smell like sulfur, but I'm sulfur. All right? And I'm 3p. You could verify sulfur is 3p. Once an atom has a certain energy, it's got access to all of the orbitals that have that energy. Listen to that statement again. Once an atom, like sulfur, has a certain energy, 3, my energy is 3. I have access to all the orbitals with that energy. Now, we said that in that row, there's a 3s and a 3p, but is there another energy level 3 anywhere on that sheet? Where? 3d. All right, now 3d is in the row below that, right? So imagine this. I'm sulfur. I've got 3s. I'm using those orbitals. If you think about how we did the configuration, my 3s orbitals are in use. I have my 3p, which are mostly used, halfway used. How many of the 3d orbitals has sulfur used? None of them, right? Because the 3d is in the row below sulfur. So sulfur, since he's got energy level 3, has access to 3d, but they're all empty. Those are orbitals that are just sitting there, doing nothing. And so sometimes sulfur slides some electrons in there. Sulfur can use those empty d orbitals to make a couple extra bonds, which breaks the octet rule, but that's why they're there. There's room to do it if you are in period 3 or physically lower on the table. So periods 3, 4, 5, 6. They can all do that, because if you're in period 4, you have an energy of 4, but 4d is in the row below you, empty orbitals. If you're in period 5, you have an energy of 5, but 5d is in the row below you, empty orbitals. So once you get to the third period or physically lower on the table, you can break the octet rule by stealing empty d orbitals. So let me show you. Let's see what this actually looks like. Do y'all see my dice anywhere? I know you don't want to tell me, but thanks. All right, so, by the way, if you're bad at drawing molecules, then you're still in a little bit of trouble. So you need to watch the Vesper videos, you too. Or really catch on now. I don't want to leave you behind. All right, so let's remember what this looks like. So bromine is in group 17 with 7 valence electrons. Fluorine is also a halogen, but there's 3 of them. What's 7 times 3? 21. Now you'll notice I'm shorthanding this. This isn't how I showed you to do it. You're supposed to make a list. But the assumption is that you know how to do this now. So I hope you're able to do it faster. But if not, go watch the other video. We are going to have 28 valence electrons when we draw this. Yeah? 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 All right? So let's draw them then. I'm going to put bromine in the middle because we always put the atom that's present in the least amount in the middle. And I'm going to bond the leftovers. All right, so let's go. Watch this, watch this. Hey, I'm going to do something weird. I want you to be weird too. I'm going to explain my weirdness. Draw it like that. A little funky. Some funky bonds. Yeah. It's going to be a good Thursday. I'm about to go off on a little tangent. All right? We're not done doing this. But I haven't showed you this before, and it's important that you know that I'm drawing this molecule on a 2D plane. This whiteboard is lying to you, because this molecule exists in the same 3D world that we do. I should be able to take this molecule off the board and spin it around and look at it from different angles. In other words, the things that it bonds to don't just go up, down, left, and right. They can also come at you. At you. Bless you. I'm going to say bless you when I say at you. Anyway, or they can go away from you. All right? Like I could look at the way this is drawn right here. I could take the molecule off the board and just turn it like this. And if I did, that fluorine would then be coming at you. And that fluorine, as I turned it, would be pointing towards the hallway. Do you understand what I'm saying? All right? And that's what these do. Listen and then paraphrase. This line, this dotted line that gets smaller, means it's going further away. And this darker line that gets larger means it's coming at you. And that's what these represent. In your own words, write that. The dotted line is just a way to represent an atom that is pointing away from you. The darkened triangle line is just an atom that's pointed towards you. Now, for now, you don't have to know how to draw them or when to draw them. I just want you to know how to analyze them when I draw them. So listen again, because one of you will ask or be worried about it. I don't want you to know, oh, am I supposed to draw a dotted line? Right now, no. I don't care if you know when. I just want you to know how to analyze it when I draw it, in regards to what it's saying about the atoms. That was my tangent. Let's go back. We're supposed to be drawing 28 to make him happy, so let's make him happy, all right? Let's make everything happy first, like we always do. I'm going to give everything its octet. I'm sure you're doing it too because you're so smart. All right, and by the way, these funky lines still represent 2 electrons. Nothing about the rules change. All right, they're still just bonds. 2 electrons in a bond. And now we'll roll the dice and see who can count how many dots I have drawn. Let's talk to person 22. See if you can count them. I'll give you a second. She says 28. Agree or disagree? How many did you get? I get 26. Now, we had a discrepancy, so let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We have never had this problem before. We've had the problem where they don't line up, but it's always been because we've drawn too many dots. And we know how to fix that. If we draw too many dots, we erase 4 dots, we add 1 bond, and yay. But this is different. We haven't drawn enough dots. That's never happened. There's no easy way to fix that. The only way to fix it is to make somebody break the octet rule. Watch. You ready for your mind to be blown? Here it comes. There's our answer. Bromine has expanded his octet. So here's the first thing that we should ask. Is bromine able to do that? Look at bromine on the periodic table. Is he in a location where he's allowed to expand his octet? Announcement. Yeah, bromine can, because bromine is in the 4th period. Remember, the rule is the elements in period 3 and any period physically below that, 4, 5, 6, 7, are able to use empty d orbitals to expand their octet. So bromine's allowed to do it. And now we've drawn 28. Bromine's got 10, yeah, but we're good to move forward. Now, because of this funkiness, we have new shapes. I taught you 5 shapes before. There's more shapes coming. Hooray. Now, I want to show you something. I'm going to do something called counting electron regions. Watch, watch, watch. I see 1, 2, 3, 4, 5 electron regions. Now, you don't have to know how to draw the flower. I'm just showing you. That's not chemistry. All right? But I see 5 electron regions, and that's how I counted them. I hope that you can see how I differentiated between them. And what I want you to know is that anytime you've got 5 electron regions like that, it is called, and whoops, I'm going to lie to you. It is called trigonal bipyramidal. Yay, a new shape, trigonal bipyramidal. Hey, there's some other things I want you to know about him. His hybridization is sp3d. The good news is I'm not going to ask you to find that from scratch on these ones, because I know a lot of y'all hate hybridization anyway. But I do want you to know come test day that if you say that something is trigonal bipyramidal, that is its hybridization. sp3d, because it's going to have a d orbital, because it's the only reason we can expand our octet is by hybridizing one of those empty d's. And then there's one other awesome thing we can do. Flip to the other side of that new sheet I gave you. All right, the other side looks like this. And you'll see that we could have been doing this last unit, but we didn't. It's real easy. Now that we are admitting that these are existing in a 3D world and looking at them like that, we can actually measure the angles, the bond angles between different atoms. For example, if you look at trigonal bipyramidal on that sheet and find them, I bet you can tell me what angles he is. What are they? Somebody!
120 and 90.
120 degrees in some places and 90 degrees in some places. All right? There's nothing to really learn there. You just need to make a couple flashcards so you can know the angles of all the shapes. But trigonal bipyramidal is always sp3d with these angles in different areas of the molecule. Now, I just threw a bunch of new stuff at you. I get that. But let's do another one from scratch, and you'll see that you have the skills already to do this. That's sulfur hexafluoride. Now, this guy should already look weird to you. Like the last example, you might not have been able to see just based on the formula that it was going to be weird, because you've seen things like BF3 before, all right, or BRF3. In regards to the numbers, it looked like it was going to be trigonal something, but when I tell you we're going to draw this, you should already have a siren go off. SF6, am I going to bond 6 things to something? Well, let's see. Valence electrons. Sulfur is in group 16 with 6. Fluorine is in group 17, but there's 6 of them. So what is his personal number?
42.
42. How many are we drawing in this molecule? 48 valence electrons. We have never drawn such a number, have we? That's exciting. All right, let's put sulfur in the middle, as of course you expect we would. And here's where we're like, okay, well now we're supposed to bond the leftovers, and there's way too many leftovers. Is sulfur allowed to expand his octet? He is. How do you know he is? All right, you say because the screen says so. No, because he's in group 3, period 3, all right, or any row below that, physically on the table. But yeah, sulfur totally qualifies to handle this load. So let's let him do it. 1, 2, 3, 4, 5, 6, Remember, those are just normal bonds. Just shows you what direction they're going. Of course, we want to make everything happy. All right, so fluorine, 8 is still the number we have in mind. I don't want you to think, oh, well, the octet doesn't even exist anymore. No, no, no. The octet governs everything. It's just we're learning that we've got these empty d orbitals by which we can sometimes cheat the system and put electrons into them since there's none there right now. There we go. Then, of course, I'm interested in how many total electrons I've drawn. And I know who knows how many I've drawn. It's person 5. Man, Aspen really owns this class, doesn't he? Aspen, can you tell me how many total electrons you see that I've drawn in my picture? 48. Perfect. If you count them all, we hit the number. We don't even have to fix anything. Any questions before I continue analyzing him? All right, well, let's see how many electron regions there are. Again, you don't have to draw this flower thing. I'm just being dramatic. But I see 1, 2, 3, 4, 5, 6 electron regions. And anytime that's true, it's octahedral. That's your final new shape for the day. This is octahedral. Octahedral will have a hybridization of sp3d2. I do want you to know that even though you're not configuring it yourself. He's hybridizing 2 Ds in order to make all these extra bonds. And who can tell me his bond angles? 90 degrees, perfect. Look on your sheet and it will tell you the angle in real life that these atoms take. You try one. I want to know everything about BRF5. His shape, hybridization, bond angles. You got this. You pause the video, unpause when you're... Help me answer some questions. How many valence electrons, I'm only talking to one person, does bromine have? Bromine, how many valence electrons? Okay. How many does 5 fluorines have? Perfect. All right, so then how many total did you put in your picture? All right, so far so good. Everybody okay with that? All right, who'd you put in the middle? All right, BR. All right, and then, uh-oh, I got too many to bond. Is bromine allowed to expand his octet? He is, right? Just got to be in the 3rd row or physically underneath on the table. So let's bond our leftovers. There's the leftovers, all right? And then, of course, I can add some lone pairs. I'm shorthanding. But I'm going to add lone pairs because fluorine wants to be happy. Now, at this step, how many electrons did we have? How many total electrons are in my picture the way I have it drawn right now? I'll give you a second. That's fine. Count. There's a lot going on, so I understand. 40. Perfect. If you count, we are at 40 right now. Are we okay with that idea? Which is the wrong number, but it's not enough. And we know if it's not enough, all we can do is add more. And again, we already agreed that bromine can expand as octet, so let's keep going. What shape is he?
Octahedral.
He's octahedral. He's got 6 regions of electrons due to that lone pair. He is octahedral. So here's a good thing. Look here. Understand this. Some of y'all tried to speed through your assignments a little bit. So you'll see BRF5 and you'll be like, I don't need to draw that. It's going to be BR connected to 5 things. Trigonal bipyramidal. Guys, a lot of stuff can happen that you can't see without drawing it. You got to draw it. It's octahedral. There's actually 6 things there, the fluorines plus the lone pair. All right? What hybridization does he have? sp3d2. What angle are his bonds? 90 degrees. How we doing? The final topic of the unit is what's called resonance. And this is something I could have introduced last unit, but I always try to watch how much I overbear you. Resonance is a very simple idea. We've experienced it before in our conversations without naming it. Resonance simply states that some molecules can be drawn in multiple ways. All correct, but drawn differently. For example, this is ozone. All right, that's ozone. I had you analyze them on their last test, actually. Now, if I wanted to draw the structure of ozone, here's what he looks like. I'm cheating for you. We're not going through the steps. All right, there's a rough version of ozone. I promise you that's the right number of electrons. Everybody's got an octet. Oxygen's not even allowed to expand as octet anyway. Resonance would be if we could draw that a different way. Follow the same rules, not add or subtract anything, but draw ozone just in a different way. And you could probably see the one change that we could make. Anybody see it? What could we do? See that double bond? Well, we could have drawn it here. All right, that lone pair would have been over here. But if I were to, don't do this, just want you to see in your head. But because some of y'all are like, oh, well, you just flip the molecule around. No, that's not what I'm saying happened. I'm saying that if we lettered these oxygens, oxygen A, B, and C, originally there was a double bond between oxygen A and B. But now there's a double bond between oxygen B and C. Well, that's different. All right? That's different. But it's the same thing, right? Different but the same. Are you with me? How many different resonance structures did we just show that ozone has? 2. It had 2 resonance structures because there's 2 ways to draw it. Let me show you another one. Here's a funky compound. You're riding with me. All right, arsenic has a valence count of 5. Iodine has a valence count of 7, but there's 3 of them, so that's 21. And then it's an ion. Hey, what does that +2 do to my electron count?
-2.
Makes it smaller. All right, remember, if we're positively charged, then we have less electrons. What's my total count here? 24. All right, this molecule would have 24 valence electrons. All right, nothing new, nothing weird yet. I'm going to put arsenic in the middle because there's the least amount of him. I'm going to bond the leftover I's. Okay. I want to make everything happy. All right, remember the octet is always the definition of happy. Hooray. My picture's got a happy molecule right now. Hey, before we finish analyzing him, is arsenic allowed to expand his octet? Look at his location and tell me. He is, because he is in period 3 or a physically lower period. But does he need to?
No.
Don't be the student that tries to always expand the octets now that you know it's possible. It's weird when you try to make 10 bonds to something that only needs 2 bonds. All right? I'm showing you something that happens a little rarer than these regular ones, so don't forget that the last unit happened, okay? Now, if I count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, I've got too many. This is a problem that we haven't had today, but we had a bunch of times last unit. You know how to fix this. If there's too many, we erase 4 dots and add a bond. But look, I want to show you the resonance. That's the whole point, right? Watch this. Erase 2 dots. I need to erase 2 more. Which eye should I take it from? It doesn't matter, right? But watch, she said the bottom one, okay? If I took it from the bottom one, there's the structure. But did I have to do that? No, no, no. Maybe you don't like the bottom one. Maybe the bottom one, you know, kissed your girlfriend or whatever. So maybe we want to do it from this guy instead. Hey, look, a new resonance structure. I just drew the same molecule in a different correct way. Is that the last way I could have done it? No! I found another one. Maybe that guy over there is even worse than the guy below. So I made the bond here. How many resonance structures did this molecule have? 3. Somewhere near where you wrote the definition of resonance, which is going to be back at the top of your notes, write down that for right now, it must contain a double bond to happen. For our purposes, resonance will happen if at least there's a double bond. Or rather, will require a double bond. I want to work out one more image with you because some of y'all have a pitfall that I see you make over and over and over again online. So let's just work this one together. All right, I'm going to do one of your polyatomic ions. Anybody tell me the name of that polyatomic ion? Say it? That was right, I think. No? It's chlorite. All right? Now, if I want to analyze chlorite, just work along with me, please. Chlorine has 7 valence electrons. Oxygen has 6, but there's 2 of them. And that -1 tells me that we have an extra electron. It's negative because we have more electrons. That's going to give me a grand total of 20. Let me know if you don't agree. I'm going to put chlorine in the middle. Let's bond our oxygens as leftovers. Let's make everybody happy. Everybody wants 8. Now, we're actually done. Nothing else needs to be, we've drawn 20. Hooray, that was easy. Here's one of the places that y'all are terrible for some reason. What shape is he? No. Linear. Linear is not the answer. Why do y'all skip bent? Why do y'all even ignore it as a shape? Linear is supposed to be your last option, and y'all never think anything's bent for some reason. The definition of bent is a central atom with 2 lone pairs. A central atom with 2 lone pairs. So quit it. Now, I want to show you this though. When you decide that a molecule is bent, it's actually not drawn like that. All right? It's actually drawn like this. And you wouldn't know to draw it initially. But once you draw it like this, you say, I think that's bent. Well, you really should redraw it like this then, because that's what bent looks like. And if you're like, well, sir, why does it matter? Well, this looks like 180 degree angles between the two outer things. And bent doesn't have 180 degree angles. What are the two possible angles for bent? Look on your sheet. It could be 120 or it could be 109.5. Do you agree? The difference between those is a hybridization of the central atom. Now look here. I know a lot of you don't like hybridization, and I'm going to step away from this problem for a second. Listen, there are some absolutes out there that I won't teach you because it's bad chemistry. But for those of y'all that like to know, well, if this happens, then this is always true. Here's one. If an atom that you're analyzing, trying to find its hybridization, has a triple bond on it, its hybridization is sp. That's always true. If you go back and look in your notes, you could find more of those because there are more rules like that. I just don't like to teach them. I want you to know the process because some of my questions will ask about the process, so you need to know it. But if you're having trouble just getting to SP, SP2, and SP3, there are faster ways to do it. I just won't show them to you like in this setting. All right, I want you to do the chemistry. But here's another one. If a central atom has four things that are hybridizing, look at that. That's 2 sigmas and 2 lone pairs. We hybridize all sigmas and lone pairs. If it's got 4 things it's hybridizing, it's automatically sp3. I know it's sp3 right away. Now we could go through the step to figure out what that chlorine is. We could do it. But I'm telling you that he's sp3. So now, based off your angles, what angle is this? 109.5. Based on that sheet that you're going to learn and memorize by Tuesday.